Good afternoon. My name is Jose Abrams Roman, and today I'm gonna be talking about my Phase B Senior Capstone project. Our theme for the whole project is the electrical system white cane. For the first system, which is my part, it's the electrical and control system. Off with the outline, the first thing we're gonna be talking about is the technology assessment. Then about the subsystem trait studies, the subsystem architecture into component, straight trait studies for critical components, subsystem risk assessment, and a complete project planning. On our technology assessment, we found five references. The first one is a bio-inspired electronic white cane implementation based on LIDAR. The second one is a design interactive white cane for visually impaired people. The third one is a detachable electronic device for use with a long white cane to assist mobility. Fourth is a stick design electronic for blind and ultrasonic sensor based microcontroller. And the last one is an aid to the blind based mobility electronics. Starting off with our first alternative for the subsystem trait studies, we're comparing and analyzing a feedback control system. This is a system whose output is controlled using its measurement as a feedback signal. This feedback signal is compared with a reference signal to generate an error signal which is filtered by a controller to produce the system controlling's input. As you can see in figure number 2, there's a block flow diagram for a feedback control system, basically um, describing what I just explained. And on figure number 1 is a proposed model with a state feedback control strategy. This strategy it's desired is that the angle of the main actuator stays in an optimal point to ensure accurate obstacle position detection, and the output of the microcontroller, which are fed to the vibrator motor and the Bluetooth module, are able to alert the user of any obstacles. Our four specifications are listed on the right, and for our feedback control system, we have an overshoot of 4%, an error of 0.02%, not percent, a precision of 98%, and a speed of 0.84 seconds. For our second alternative, we had a feed-forward control system. For this control system, it passes a controlling signal from a source in its external environment to a load elsewhere in its external environment. This is often common signal for an external operator. And you can see it better described on figure number 3, where there's a block flow diagram for a feed-forward control system. I tried looking for an application with a feedback control system applied to our project, but the two typical and most used control systems are the feedback and the sequential. So following on some other products that I found on the internet, our specifications can conclude that the overshoot is a 4.2%, the error is a 0.05, the precision is a 95%, and speed is 0.87 seconds. Our third and final trait study alternative is a sequential control system. This control system is an individual, it separates in individual steps that are proceed in a predetermined order and in a progression from 1 second steps to the one step bricks to the next step, depending on the defined conditions being satisfied. And figure number 5, there's a block diagram for a closed loop control system for a disk drive for a better understanding of the mechanism of a sequential control system. And on figure number 4, we can see a control system for a camera sensor smart cane. As you can see, we have the controller, which is a Raspberry Pi 3, the processor, which is the vibrator sound mechanism, and on the bottom we can see the sensor, which is in an infrared. For the specifications, this control system have an overshoot of 5%, an error of 0.04, a precision of 96%, and a speed of 0.90 seconds. After applying our system trait study decision matrix tool, which is the racing weighting, I divided each part equally on weight, and the best fit for our project and the best fit for us to conclude, it's the best one is a feedback control system. Entering is what's gonna be the subsystem architecture into components. My hierarchy diagram has three main components. The first one are the sensors, second one microcontroller, and third one the vibrator motor. Here we can see the subsystem architecture into components. As you can see, we have the problem stated and two figures. For this controller, there will always be a steady state error, and in order to achieve zero state error, an integral must be added. As you can see in figure number 7, there's a block flow diagram for this problem, and where Ti, Ta, and To are the desired atmospheres and output temperatures, being Kp and Kr are the proportional and internal gains. On figure number 6, we can see a flowchart for the program logic, and we have to calculate these three variables that we are searching for, sorry. For our straight study for critical components on the sensor selection, our first section is an infrared sensor. As you can see, we listed the specification starting with the operating voltage, the detection angle, the detection distance, the supply current, and the weight. The first one is an infrared sensor, the second one is a proximity sensor, and the last one is an ultrasonic sensor. And after applying the weighting, we can conclude that the best fit for this project is an ultrasonic sensor. For the microcontroller selection, we decided to go with the PIC controller, a Raspberry Pi, and an Arduino Uno. And we listed seven specifications, being the operating voltage, the flash memory, clock speed, weight, pin count, RAM, and 1 for analog or 2 for digital. And after applying its weight, we can conclude that the best fit for this project is the Raspberry Pi. And for the vibrator motor selection, we decided to go with the vibrating mini motor disc, the cylinder vibrating motor, and the micro vibrating motor. And our specifications are the diameter, voltage, currents drawn, weight, and related speed. After applying all the weights and the values, we established that the vibrating mini motor is the best fit for our project. Entering into what's gonna be the subsystem risk assessment for my subsystem, which is the electrical and control system. We have that the first risk is a bad signal between all components, and our strategy is to enhance the system availability by reducing sharp edges and improper bends, resulting in a safe wire route. The second risk title is an electrical shock and burn from a contact with live parts. So our migration strategy is to we must make sure that the electrical installation and the electrical equipment is suitable for its intended use and the condition in which it's operate and is only used for its intended purpose. Then we have the battery life problem. Our strategy is to utilize a chargeable battery with a minimum of 200 to 400 charging cycles. The next risk title is a sensor detection error, which we can properly attach sensor in the correct angular position with no nearby interference. And our last risk is the vibrator turning on when it shouldn't. And we must ensure that all current flow is in its proper direction. For the subsystem risk on the Sophia diagram, we can see that the first and the third are the first one is a low impact of occurrence and probability. The second one is a medium. The third one is a medium. The fourth one is a medium, and the five is a medium also. And for my project planning, as you can see, the week 1 of June, I'm gonna be working on the interface diagram and the detailed analysis design studies for the control system. On week 2, I'm gonna be working on the design to specification and drawing in electronics. And on week 3 and 4, I'm gonna be working on the verification electronic control system and my project planning. For the deadline of phase C1 presentation is gonna be August 12th, 2021. Thank you for your attention.